Math 230, Cuesta College. I'm Joe Vasta, and today we're going to cover section 4.3, changing bases. So what's this all about, changing bases? Well, first of all, we're going to start with base 10, because base 10 is the base that we use. So base 10 uses 10 digits. And those are the digits, the symbols that we use for base 10, 0 through 9. And if I were to write the number 10, I would be recycling some of the digits, because 10 is a 1, 0, and 11 is a 1, 1. So all the other numbers that we use, we're just recycling these guys. So we use 10 digits. Now we write our numbers in terms of powers of 10. So for instance, if I put this number down like this, which is 7, 8, 6, 3. Well, remember, we did this Roman numerals. We talked about Roman numerals being a positional system, and so is our system, a positional system. So it does matter that the 7 is there. We can't just swap the 7 and the 8 or we'll get a different number. So what does it mean? This is 7,863, so hopefully we knew that. But the 3 happens to be in the ones place. Now what I'm going to do, some of you are going to think, oh Joe, I already know all this and this is super boring. But remember what you're watching. You're watching a math video. Of course it's going to be super boring. But what I'm doing here, even though you might already know it, when I get to the next example, you'll be able to look back at what I did here and go, oh, that's why he did that. So there's the ones place, and then the 6 is in the tens place. The 8 is in the 100s place. And the 7 is in the thousands place. So that's how it works. And when you do this, it's really like this. I mean, what are we doing? We're just looking at this number. But it's like you have 7 thousandths, 7 times 1,000. And, there's the plus there, you have 8 hundredths. And you have 6 tens. And you have 3 ones. So maybe we should try to make some sort of connection. First of all, we're going to say the plus sign is and. And let's call these ones, let's call them pennies. So we'll say this is pennies. So you have 3 pennies. And then the tens we're going to call dimes. You have 6 dimes, and the 100ths we're going to call dollars. Dollar bills, whatever. You have 8 dollar bills. And the 1,000, well, those are $10 bills. $10 bills. How many $10 bills do you have in this example? 7 of them. So think money, and the next example will click a little better than just looking at numbers. So when we have 7,863 cents, you can think of it as you have 3 pennies, 6 dimes, 8 dollar bills, and 7 $10 bills. Now before we move on to the more uncomfortable material, let's take a look at these. These numbers here form a geometric sequence. 1 times 10 is 10 times 10 is 100 times 10 is 1,000, etc. But we could also write these as powers of 10. So 10 is 10 to the 1, and then this guy right here. And this is what we mean by this. We write numbers in terms of powers of 10. So look at this. This is 10 squared. That's 100. And then the thousandths place is really 10 cubed. And the ones place is 10 to the 0. Okay, so some people like that, and other people are just like, yeah, I don't like that as much, and so you could take it or leave it, the red part. Now, before we get into the new stuff, okay, this is stuff we already knew here, okay? I mean, I put this analogy with pennies, dimes, dollars, and $10 bills, but it's stuff we already knew. Forgot to show us the puzzles here. Okay, puzzle number 1, there are 10 kinds of people, those who know binary and those who don't. Okay, so what's up with that statement? A Roman walks into a bar, holds up 2 fingers, and says, 5 beers, please. Okay, so some of you are like, oh yeah, I get problem number 2 or puzzle 2. We'll come back to the end with those. We'll also, at the very end of this lecture, explore something called smart cards. So we'll see what is so significant about those cards. So we'll do all that at the end. Okay, so we have this written down here. Now we're going to go ahead and explore a different base. Okay, so we're used to base 10. We use base 10 probably because we have 10 fingers, and so that's how it came about, why we chose 10 symbols. Well, let's look at base 5. Base 5 only uses 5 digits, not 10. And the 5 digits that we use for base 5 would be 0, 1, 2, 3, 4. So if you wanted to write a 5 in base 5, you would have to use some of these symbols here. Just kind of like with base 10, you wanted to write the number 10 in base 10, you'd have to use a 1 and a 0. And we'll get into that, you know, like how to switch things from one base to another base. Okay, we write numbers in terms of powers of 5 for base 5. So what I'm going to do is put a number down like this. This is 2, 4, 0, 3. Okay, so I'm going to tell you that this number is in base 5, and we've used symbols up there. Now, this will get really confusing because a lot of you are looking at this and you're saying 2,403. So to indicate you're in a different base than base 10, we're going to put parentheses around the number, and then down here we're going to tell you what base we're considering when we look at this number. This is base 5. Okay, so base 5 is going to be similar to base 10 in the way we start off. Remember, with base 10, that was the ones place. Well, with base 5, the right digit is also in the ones place. Now remember, with base 10, we said that was a geometric sequence. I went 1, 10, 100. Well, we're going to have the same thing, except it's going to go 1 and not 10, but 5. So you have the ones place, you have the fives place, and then you go 5 times 5 is 25. You have the 25s place. That's weird to have these places instead of, you know, like tens and hundreds. This is 5 and 25, and then you multiply 25 by 5, and the next one will be 125. And that's that place. And so that's what we have. Now, in terms of powers of 5, well, this is kind of cool to see. You have 5 to the 0 there. No, what am I saying? 5 to the 1. Okay, so we have 5 to the 1, which is that one there, and then 25 is 5 squared, and 125 is 5 cubed, and then 1 is 5 to the 0. So you can see the similarities between base 5 and base 10. We're more used to base 10, so we're comfortable with that, but with base 5 we're like, wow, this is crazy. Now, let's use our analogy. With this one, we have pennies, and then this is going to represent not dimes, but there's 5 of them, so those are going to be nickels. And then 25 would be quarters. Now it gets a little weird here because we don't have a $1.25, a $1.25 coin or piece or whatever, but I'm going to say let's pretend for the moment that we do. So suppose we have this coin, maybe it's bigger than a quarter, and it represents $1.25. So basically, I put that up there because it helps us a little. This tells us how much of each of these coins we have. We have 3 pennies, 0 nickels, 4 quarters, and 2 of these weird coins called $1.25. And so let's write that below, just like we did with the other one I have. 2 times 125. And we're actually seeing how much cents we have. That would be C-E-N-T-S. So we have 2 of those, and we have 4 times 25, and that's what the pluses represent. We have 0 times 5, and we have 3 times 1. And don't you see, that's kind of what we did on this problem above. When we were doing base 10, well, those were powers of 10. 1, 10, 100, 1,000. Now we're doing base 5, and these are powers of 5. So we have, you know, the 1, the 5, the 25, the 125. So let's go see how much cents we have in terms of money, how much money we have. 2 times 125, so I'm going to add this up on the side here. So this is going to be 250 plus, this guy right here is 100. There's a 0, which I don't need to write. And 3 times 1 is 3. So I add things up. I don't have to carry it all here. Looks like this is going to give me 353 cents, and that's what we have. So 2403 base 5 is really 353, which is a base 10 number. So when you're writing base 10 numbers, you don't need the parentheses because that's the base we use. Okay, so this is really weird if you've never seen this before, because you're probably thinking, wow, why would you even want to do this? Well, without change of base, because that's what we're going to be doing. We changed from base 5 to base 10. Without this skill, we would not have computers, cell phones, digital stuff. I mean, our world would be a lot different without different bases. So let's look at some places where this is used, and then we'll work on some problems. This list doesn't cover everything, but base 2, base 4, base 16, they are found with computers. And we're going to learn this in a future section, that base 2 and computers are very natural. Base 2 only has 2 symbols, so you can think about what those would be. We'll do one of those later. Base 3, some weighing problems, math applications, and some weird kind of circuits will use a base 3 system. Base 4, Shumashin languages originally used a base 4 counting system. I think most or all of those Shumashin languages. So I know some different groups used a base 5 system. The Roman numerals are kind of a base 5 system because at 5 you have a new symbol, but that's not, you know, that's kind of a weak connection there. Base 10, well, we use this. Base 12, well, that seemed appealing to some people because a dozen is 12, a gross is a dozen, which is 12 squared or 144. And so there were some people who really liked base 12 and thought that perhaps maybe we should use base 12. And here are some people who thought we should. Herbert Spencer, John Quincy Adams, George Bernard Shaw. Base 20, the Aztecs used that, and the Mayans. Base 60, Babylonians. And these are ancient groups. And you can see that because we have 60 seconds is a minute, 60 minutes is an hour, and that's based on the Babylonians. Also some angle measure as well. 60 goes into things nicely with angles. So those are just some applications. Let's go ahead and do some problems. So you might be thinking, well, Joe, we don't know how to do these problems, and all we did was change something from base 5 to base 10. How am I going to change this base 3 to base 10? Well, let's go ahead and, you know, we'll do this one together, and then maybe after I finish this one, you can kind of see if you can do that one on your own. Okay, so I write down this number, 1, 0, 2, 1. Okay, so now I know that it's base 3, so I could put the parentheses there. I'm not going to this time. So what I'm going to do right above that is I'm going to go ahead and say that this one is in the ones place, and because I'm changing from base 3, the next one's going to be not 10s, not 5s, but the 3s place. So I go 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. So you have the 27s place. Okay, so that's how I do it. Then I have 1 times 27. So there's 127. And there's 0 9s. And there's 2 3s. And there's 1 1. You can look back on that last example that we did and see that that's exactly what we did, except on the top we had 1 5 25 125. But that was because we were working with base 5. This is base 3. Notice base 3 only uses 3 symbols, and that would be a 0, 1, and 2. And you see those up there. Now if we had something that said 1, 0, and then there was the symbol for 7 there, and then a 1, we know that the problem was a bad problem. Okay? So let's go ahead and add these guys up. 1 times 27, 0 times 9, which does not have to be written. Whoops. 2 times 3, and 1 times 1. So this one we carry the 1, and that gives me 14, and then 2, 3. So this is 34. So what it means is 1, 0, 2, 1, base 3 is really 34. And when you have a number written in another base, like this one, we would never say 1021, because already when you say 1000, you're already saying something that's a base 10 number. This is a base 3 number. So this equals 34. So why don't you pause the video, see if you can do this one. Okay, 574 base 8. 574 base 8. So I'm going to put the 5, the 7, the 4. And I'm trying to change it to base 10. So we have the 1's place. And then, see, it's base 8. So we have the 8's place. 1 times 8 is 8. 8 times 8 is 64. Now for those of you who like the other way, I mean, we're still going, this is still 8 to the 0, 8 to the 1, 8 to the 2. You don't have to write that. There are some people in this class who are like, no, I like writing that, and you'll write it when you do your problems. This one is 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3. Okay? So some people like to write those because they see the pattern a little easier than this right here. Well, in any case, you multiply. So you go, there's 5 64s, so 5 times 64, and plus there's 7 8s, and there's 4 1s. Okay, so I'm going to go ahead and do this a little off to the side here. 64 times 5. So that is 20, carry the 2, 30 plus 2 is 32. Okay, so this is 320 plus 7 times 8 is 56. Plus 4 times 1 is 4. Okay, now I'm going to add these numbers up. 6 plus 4 plus 0, that is 10. 5 plus 2 plus 1 is an 8, and then the 3. So this number, 574 base 8, is really 380. You can also see that base 8 has 8 digits that we can use. 0, 1, 2, 3, 4, 5, 6, 7. And you see some of those that I just said right there. Now here's the deal. Base 8 has a name because it is a common base. Base 8 is also called octal. Okay? You know, octopus, we get OCT for, you know, the 8 tentacles. Well, octal means base 8. Okay, now all the bases have names, but I'm going to just give you the names of the more common ones that are used. So this is what you're going to be doing in your homework. I think the best thing to do is to do some more problems. So here's 3 more problems. You might decide to pause the video and see if you can do these on your own. But here I go. 403 base 6. So I put the 4, the 0, and the 3. And then right above it I put the places, with the first place always being the ones place. So there's 1, and then this is base 6. So 1 times 6 is 6, and 6 times 6 is 36. Now you can write 6 to the 0, 6 to the 1, 6 to the 2, but I'm not going to write that. Okay, so now we have to multiply. We have 4 36s, and we have 0 6s, and we have 3 1s. So 36 times 4, I'll do that down here. I don't have a calculator nearby, so we have 24, 12, 13, 14. We have 144. So the first one gives me 144 plus 0 from that, plus, oh wait, I don't have to put another plus sign, do I? Okay, that looks like a minus now. Okay, get rid of that. So this gives me 147. So the answer to this problem is 147. So we finished problem 3. Problem number 4. We have this 1011. So there's just zeros and ones there. This is base 2. We have to figure out what this number is in base 10. The instructions are change to base 10. So I write down this number, 1, 0, 1, 1, and then right above, on the right-hand side, we put a 1 there, just like we did over there. This is base 2, so now I'm going to multiply by 2 each time. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. So in base 2 I have the 1's place, the 2's place, the 4's place, the 8's place. The multiplication for base 2 is not that bad because you're either multiplying by 1's or by 0's. And multiplying by 1's isn't that bad. So I'm going to write this out. This might be the last problem I write this out on. I don't know. I have 1 times 8 plus 0 times 4 plus 2 times 1 plus 1 times 1. No, that's all together. And, you know, if I was a purist, I would have put the 1 over here and the 2 over there, but it doesn't really matter in terms of the math here. This is 8 plus 0 plus 2 plus 1. So this number, which is a base 2 number, is 11. And we're going to see that base 2 is connected with computers. And so in the computer, if you want it to hold the number 11, you'd be using a 1011. And you might be thinking, well, how does that work? In the future section, we'll see. Now, base 2 has a name. It's called binary. Base 10 has a name, and maybe we should have said it right off the bat. That's called decimal. You know, and you think of the decimal point, but it's called the decimal system. Now, let's go ahead and see if we can do number 5. And hopefully you're pausing the video from time to time to see if you can do these problems. I'm going to write down 1, 1, 1, 0, 1. And right above it, I always start on this right top part, and I always put a 1 there, and then this is base 2, so we're going to do the same thing. Times 2, times 2, times 2, times 2. Draw a line. I'm going to multiply. I'm not going to write all that out where I go 1 times 16, 1 times 8, so I'm just going to write a 16 plus an 8 plus a 4 plus a 0 plus a 1. So when I add that all up, look, this gives me 16 plus 4. So I'm looking at that. That's 20. And then we have an 8 plus 1, so this is 29. So that's how you change other bases to base 10. But there's going to be a snag when you do your homework, because sometimes the weird base will be greater than 10. And so let's go ahead and see what you do when the base is greater than 10. And we'll encounter one of those bases because it's a common one, but you can generalize to, like, you know, like we're going to cover base 16, but you can generalize that to base 18 or base 13. So base 16 uses 16 digits or 16 symbols. Let's write those symbols down, okay? So I'm going to write them down here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 10 symbols there. Now, you're saying, well, we need to go 16. So, you know, one thought is, hey, let's put a 1 and a 0, but we're recycling those and we can't do that. So we need a new symbol. I've seen different books do some weird things. Like I see some books, they put a T for 10 and an E for 11. But the problem is when you get to 12, that starts with a T again. You can make up your own symbols, but no one's going to understand what you're doing. You could put a happy face for 10 and a sad face for 11 and some of your other lucky charms until you get 16 digits. Well, what they do in the computer science world is, what is going to be a 10? The letter A. So that right there is 10. I'll spell it out. And then the letter B is 11. C is 12. D is 13. E is 14. How many do we have here? Because we're only supposed to have 16. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I need one more, which would be the letter F. And that's going to stand for 15. And just like base 10, you know, base 10, the 10 had to be recycled, and base 5 has to be recycled, the actual number 5. With base 16, the number 16 is not going to be any of these new symbols, it's going to be recycled symbols. So this is base 16. Base 16 has a name. Base 16 is called hexadecimal. Now decimal, that was base 10. And you might remember this, hex. Like a hexagon has how many sides? 6. So this is like saying 6 and 10, which is 16. So hexadecimal. And this is important that I tell you this. So there's 4 of them that we should know when we do our homework. Octal, base 8. Binary, base 2. Decimal, base 10. Hexadecimal, base 16. It was important that we went over this before we did the next problem, because the next problem is this right here. Well, the next 2 problems. (5e). So I'm going to go ahead and write that down. 5e. Because I'm changing from base 16 to base 10, the instructions are changed to base 10. I always put the 1 there. Now because this is base 16, I'm going to go 1 times 16, which is 16. And I do the same thing I did on the other problems. But there's a problem here. I mean, I'm going to go like 5 times 16 plus e times 1. Okay, so this is where we have to stop and go, wait a minute, what's an e? An e happens to be 14. You can look on that other sheet there. So e is a 14. So this is going to be 14 times 1. Okay, so I'll do 16 times 5 over here in the corner because I don't have a calculator on me. You're like, you're a math teacher. Why wouldn't you have a calculator? I just don't have one. I'd have to walk across the room to get the calculator, and you know, I'm feeling very lazy today. So look at this. I have 80 plus 14, and 80 plus 14 is 94. So if you have a hexadecimal number that says 5e, base 16, the answer is 94. Why don't you pause the video and see if you can do this one on your own. It's a little more challenging because there's 3 symbols. Okay, so my 3 symbols are 1, A, 2. I've got the ones place. 1 times 16 is 16. 16 times 16. I'm going to go ahead and do that off to the side. So this is 36, 6, 7, 8, 9, and then put a 0 there. And then 1 times 6 is 6. 1 times 1 is 1. 256. So this is 256. So here's the deal. This A is really what? So I'll go back and show this piece of paper that we have. The A is a 10. So this A is really a 10. So this is 1 times 256 plus 10 times 1, 6, or 10 times 16. And then plus 2 times 1. Okay, so let's write this out. This is 256 plus 160 plus 2. So 256, I'm just lining them up vertically so I can add them more efficiently. I have an 8 there, and then 5 plus 6 is 11, carry the 1. 2, 3, 4. So the answer on this one is 418. Okay. Now, I wasn't planning on doing this, but I want to do this because you might think that whenever I ask you to change from base 16 to base 10, you're always going to have a letter in there. So this one I'll call number 8. Well, this one doesn't have a letter, but it could still be written in base 16. Now, we want to say 21, but don't do that because this is base 16. We're going to say 2-1. So what is 2-1 in base 10? So I'm going to write 2-1 here, and I know what you're thinking. You didn't give a lot of space to do this, but I don't think we need that much space. And then we're coming from base 16, so we have 1 there and a 16 there. 2 times 16 is 32. 1 times 1 is 1. So the answer to this one is 33. I wasn't planning on doing one of these, but as I was doing this, I was thinking, like, some people might think that anytime we're doing base 16, that it's always going to involve letters. Sometimes it might involve letters, and sometimes it might not. I mean, sometimes it involves 5s, and then the other problems didn't have 5s. So that is how you change from a weird base, like base 16 or base 5 or whatever base we were doing. That's how you change to base 10. It's always going to be the same procedure. With base 16, there is that hiccup when you do see a letter, but just practice your homework. And you know, if you do your homework, when you get to the test, it shouldn't be that big of a deal. Okay, so we can go one way. Now we're going to go the other way. Meaning, you know, like we had a 94 was our answer here. We're going to learn how to go from base 10 to a weird base like base 16. Okay, but we're not going to start with base 16. I think we'll start with base 5. So here it is. Change 238. We know that's base 10 because we don't have parentheses around that. So that's 238. Change that to base 5. Okay, well, what we have is we have 2 methods. So I'm going to show you both methods, method 1 and method 2, and you know, when you do your homework, you can pick the method you want to do. Well, base 5. What I'm going to do for method 1, and some of you will like this the best, is I'm going to put these little containers. And the first container I'm going to call 1. Okay? The container that I put to the left of it, I'm going to call that 5. Now why? Because this is base 5. And then I'm going to keep making containers. So this one here is going to be 5 times 5, which is 25. So it's like I have my place value for base 5. I'm going to keep going. This bucket right here is 125. How did I get that? I went 25 times 5. The next bucket, well, what's 125 times 5? I'll do that right here. So this is 25. And we have 10, 11, 12, 5, 6. So this is 625. 625. Okay, I'm going to stop right there. It's a good idea to stop when this number is greater than the number you're changing. And you're going to see why. Okay, so think of like you're buying like some, I don't know, just some item. Let's talk shirts. Okay, I don't mean to sound like an economics instructor, but let's say they always like to say widgets, don't they? Or something. I haven't figured out what those are. But you're buying shirts or any other item that you can think of. And sure, you can go to the dollar store and get them, but they might fall apart faster than if you put more money in there. Now, I don't know if I'd pay $125 for a shirt, but the deal is with method 1, you have $238. $238. And your strategy is to always buy the most expensive thing. And so some of you are like, well, what about $625? Can we put that on the credit card? No, we're not doing credit cards. You have to buy it with this. So the most expensive shirt that I can buy is from this rack here, and maybe it's not on a rack, but it's $125. So I'm going to buy one. Minus 125. So this gives me a 3 here, and a 1 there, and a 1 there. So now I have $113 left, and I have one of those shirts in that cart. Okay, now with $113, can I buy another one of those shirts for $125? And the answer is no, I do not have enough money. So I'm always going to buy the most expensive thing. I can buy at 25. And some of you, because this is 25 and it's kind of simple to do the arithmetic, you see that you can buy how many of these 25s? Well, 4 of them. 1, 2, 3, 4. Now some of you would just go minus 25, then minus 25, and minus 25, and minus 25. I'm going to go minus 100 because I saw that 25 times 4 is 100 and I can get 4 of those. Now I have $13 left. Can I buy another 25? And the answer is absolutely not. I have to now buy the cheaper item, which is a 5. Well, how many of these 5s can I buy? I could buy probably 2 of them. So I'll put 2 of these cheaper shirts in the cart for those items there. So I just spent $10. And now I have $3 left. And I have to use up all my money. So I'm going to buy 3 of these shirts from the dollar store. And now I subtract, and the name of the game is to get down to $0. And you're like, but I didn't need that many shirts, or I don't like to buy really expensive shirts. Just stop complaining and do the problem. So look what I have. I have my answer. What is my answer? You put numbers right above each of these. So look, there's one thing in there. So 1, 4, 2, 3. We were asked to change to base 5, and we did. And you can think back, like if you wanted to change this to base 10, look, there's 3 1s and 2 5s, which make 10, and 4, you know, and you can see that would actually put you back at 238. But this is how we change, or one method of changing numbers to different bases like base 5. Okay, now let me give you the other method, method 2. So what you want to do with method 2 is start kind of low, and you put this number, 238. 238. And what you do, so some of you are like, okay, yeah, I'm out of here, I'm just going to do method 1. You see that long division, and you're like, forget it. Shopping is going to be a lot easier for me. Well, anyway, so there's going to be some people who like method 2 better. I'm going to put the base I'm trying to change to right there. 5 goes into 238. Okay, 5 goes into 23 4 times. 4 times 5 is 20. We subtract, we get a 3. Bring down the 8, 5 goes into 38. 7 times 5 is 35. We subtract and we put a 3 there. Now it's important, this is our remainder, we're going to go remainder 3. Now the deal with this is even if your remainder was 0, you still want to write it. Now you put 5 into that. And you keep putting 5 into the quotient until you cannot put 5 into it anymore. So how many times does 5 go into 47? Well, 9 times with the remainder 2. Now if you had to bring that off to the side to do that, there's nothing wrong with that. Now, how many times does 5 go into 9? Because 5 can still go into that. It would be 1 time with the remainder 4. Because 5 cannot go into that top quotient, we're done. The important thing to do is you pick it up right from there, from the quotient. You don't just start at the 4 and you head down the river. And when you head down the river and you say the remainders, look what you have. You have a 1, 4, 2, 3. And so that gives you exactly the same answer. So method 2 yields the same answer. So pick your method. Maybe you'll do both methods on a few problems and then pick the method you like better after you do a few problems. But that is how you change to base 5. The reason this works, there are 47 5s in 238 with 3 left over, and there are 9 25s in 238, and there's 1 125 in 238. So it works. We're not going to get into the whole proof of it, but this is very legitimate and will always get you correct results. There are advantages with both of them, and I'm not going to say them yet. We'll move on to the next problem. So problem number 2. Change 135 to octal. What is octal again? Octal is base 8. So why don't you pause the video and see if you can do this problem. Okay, I'm going to go ahead and do this problem. I'll do both methods. So, you know, maybe if you already know which method you like, you could just skip forward past the method you don't like here. Method 1, the shopping method. Octal is base 8. So I have a 1 cart, an 8 cart, because of base 8, and then I'm going to go 8 times 8 is 64. And then the next one, well, I'm not going to even be able to afford it. And some of you are like, well, I don't believe you, so watch this. 64 times 8, 32, carry the 3, and then we have 48, 49, 50, 51. 51. I'll write it in red because you can't afford it. 512. How much money do you have? You have $135. $135. So what I'm going to do is I'm going to buy a 64 item. Subtract. Okay. 5 minus 4 is 1. 13 minus 6 is 7. So I could actually buy another 64. So I'll put another one in the cart. So there's the first one, here's the second one. So subtract 64. Let's see, that gives me a difference of 7. Okay, I cannot buy an 8, but I can buy 7 of those guys right there. So let me put 7 of them in the cart. 1, 2, 3, 4, 5, 6, 7. It's overflowing. And so I've just paid the money. I'm down to 0. I'm happy with that. I've got to write the number. Now we don't want to write 27. We want to write 2. How many items are in this cart? 0. And how many items are in this cart? So the camera just turned off, but I've turned it back on now. So 207. And this is base 8. So that is method 1. Method 2 is long division. Long division, we take this number 135 and we put 8 into that. Now the long division, the first one's always the worst because the other ones above are going to be smaller numbers that you're dividing into. So 8 goes into 13 one time. 1 times 8 is 8. Subtract, we get a 5. Bring down the other 5. 8 goes into 55. Well, not 7 times, but 6 times. 6 times 8 is 48. We subtract, and we end up getting a 7. 16, remainder 7. See what I mean? So now we're going to go ahead and we're going to put the 8 into the 16. 8 goes into 16 2 times exactly. You still have to put the remainder. The remainder is 0. Look what happens when I go down the river. I end up getting 207, which is exactly the answer that I got with the shopping method. Okay, so this is a little bit more challenging to convert from base 10 to a different base. So in this lecture, that's why we do lots of practice. Change 53 to base 3. So pause the video and see if you can do that. I'm going to go ahead and do both methods. Method 1. Shopping method. Base 3. That's what I'm thinking of when I'm putting my bins here. So we have 1, 3, 9, because 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is going to be a lot bigger than 53. So I'm just going to stop right there. And now I have my $53. Okay, I think I can buy a 27. So I put 1 in the cart. So let's see, 13 minus 7 is 6. I've just borrowed from the 5, by the way. So 4 minus 2 is 2. Can I buy another one of those expensive items? And the answer is no, because now I only have $26. So what do I want to do with my $26? Well, I could buy 2 9s. I could buy 1 9, subtract it, and then you'll find that you can buy another one. So if I've just bought 2 $9 items, I've just spent $18. And so this gives me $8 left over, which I cannot buy another 9. Well, how many 3s can I buy? I can buy, if I bought 1 3, I'd have $5 and then another 3. So it looks like I could buy 2 3s. So I've just spent $6. And now I have $2 left, and so I'm going to go ahead and just invest in these dollar store items. And we've subtract that. I have no money left. So my answer then is going to be 1, 2, 2, 2. 1, 2, 2, 2. And this is base 3. Now, if you ever get an answer on a problem like this where it says like 1 and then there's the symbol for 3 and a 4, then you know something happened. Maybe you were super tired when you were doing the problem or something happened. So base 3 should only have 0s, 1s, and 2s. Okay, method 2. Method 2 is the long division. 3 goes into 53. 3 goes into 5 one time. Subtract. 3 goes into 23 7 times. So there's a 21. Subtract. The remainder is 2. 3 goes into 17. Well, we know that 3 times 5 is 15, so it goes in 5 times with a remainder of 2. 3 goes into 5 how many times? Well, 1 time, and it's going to have a remainder of 2. Start with the 1. Your answer is 1. 2, 2, 2. Go down the river. And that's exactly what we have right there. Let's do a few more of these problems. Problem number 4. Change 248 to base 6. I'm actually going to go method 2 first. So maybe you're pausing the video to see if you can do this problem. Choose your method. 648. I'm going to go ahead and put 6 in there. 6 goes into 24 4 times. You subtract and get a 0. Bring down the 8. 6 goes into 8 1 time. 1 times 6 is 6. Subtract, get a 2. So we have 41 remainder 2. 6 goes into 41. Well, 6 times 6 is 36. And what is that difference between 36 and 41? It looks like that difference would be 5. So you might think, am I done? Because there's a 6 there. Well, can 6 go into that? And the answer is yes. You're done when the number is less than the number you're dividing. Okay? So 6 does go into 6 1 time. And here's the mistake people do on the test. They go, oh, the answer is 152. But you forgot to put the remainder. Remainder 0. So if the remainder is 0, it's essential that you put it. So my answer then is 1052. 1052. This is base 6. Why don't we go ahead and do method 1. So method 1 says we're going to go shopping. There's 1s, and then we use this right here. 6s. 1 times 6 times, so 1 times 6 is 6. 6 times 6 is 36. 36 times 6. So 18, 19, 21. So 216. We have 248. I'm not going to go any more because I won't be able to afford it. So 248. We're going to buy one of these items. It's very expensive, so we'll put it in the cart and we'll handle with care. And then we subtract. We only have $32 left. So I cannot get another 216. In fact, I cannot get a 36 item. But I could get a few of these guys. In fact, how many 6s could I get? Now, really, notice what you're doing. When you're saying, how many 6s can I get? You're actually putting 6 into 32. So you're doing some sort of division in your head, unless you're the person just going minus 6, minus 6, minus 6, minus 6. I mean, whatever. But, I mean, for those of you who are like, oh, look, I can get 5 of them. It's because you did some division in your head. And 5 6s. So what? The money you just spent there was $30. So then you only have $2 left, so you're going to buy those items there and bring it down to 0. Now look above each bin. You have a 1, a 0, a 5, and a 2. And isn't this exactly what we have right there? Let's do a few more of these problems. We still have to do the ones with base 16, so yeah, we'll do this one first because we didn't do a binary on this type. Change 109 to binary. And I will use method 2 first. You can pause the video and pick a method you want, or here's something even funner. Let the video go and race me I know that sounds kind of dumb, but you could do that. Okay, so I'm going to do long division 109. Binary is base 2. So 2 goes into 109, 2 goes into 10 5 times. 5 times 2 is 10, subtract, you get a 0, bring down the 9, 2 goes into 9, 4 times 2 is 8, subtract, you get a 1. The 1 is important, it's the remainder, 54, remainder 1. 2 goes into 54, well I know 2 goes into 50 25 times, so 2 goes into 54 probably 27 times with the remainder of 0. 2 goes into 27 times. Well, this is an odd number. Notice whenever you have an odd number, the remainder is 1, and when you have an even number, the remainder is 0. So 2 goes into 27. That looks like it's going to be 13 times with a remainder of 1. 2 goes into 13 6 times with a remainder of 1. 2 goes into 6 3 times with a remainder of 0. 2 goes into 3 1 time with a remainder of 1, and then 2 does not go into 1. So you are done with this problem if you've done it this way. And you start off at that top 1, 1, 1, 0, 1, 1, 0, 1. So let me write that down. So this is 1, 1, 0, 1, 1, 0, 1. There's your binary for the number 109. Now method 1 is the shopping method. You set up your buckets. You have the 1 bucket, the 2 bucket, the 4 bucket, 8, 16, 32, 64. So how I'm getting this is I'm multiplying by 2 each time. Or I could say I'm doing powers of 2. 64 times 2 is 128. But the deal with that one is you can't afford it. So I have $109, and I didn't leave myself much space here. I can buy a 64. So this is a 5 and this is a 4. So I just bought one of those. I could buy a 32. So I go ahead and make the purchase. And now I have $13 left. Let's put the 13 up here. I cannot buy a 16. Here, I'll just put an arrow here. I just ran out of room here, kind of. But I can buy an 8. So I'm going to go ahead and buy an 8. I have $5 left. I can purchase a 4. I cannot purchase a 2, but I can purchase a 1. And I'm all out of money. And what I have here is I have 1, 1, 0, 1, 1, 0, 1. And that's exactly what I had when I did long division. Now I know you might be thinking, well, isn't there like a 0 right here? Well, yeah, I mean there is. We usually don't do that. We usually don't say, hey, my number is 13 and then put a 0 in front of the 13. Yeah, that still means 13, but usually we just don't do that. Unless you're this, then that's all right. Let's go ahead and do another example where we change a number to base 16. Okay. I'm going to go ahead and do method 2. Now, there is a little thing that comes up on this, so we got to be careful. So method 2. 3,391. I'm going to put 16 into that. 16 goes into 3. Now, 16 goes into 33. Yes, it does. 2 times. 2 times 16 is 32. Subtract. We get a 1. Bring down the 9. 16 goes into 19. 1 times 16 is 16. Subtract. We get a 3. Bring down the 1. 16 goes into 31. Almost 2 times, but it's just going to be 1 time. 1 times 16 is 16, and we're off the paper. Subtract. Your remainder is 15. So I have 211, remainder 15. I'm going to go ahead and put 16 into 211. Now, there's a problem here. I don't have room underneath, so I'll go over here. 16 goes into 211. 16 goes into 21. One times 16 is 16. We subtract, we get a 5. Bring down the 1. 16 goes into 51. I think it's 3 times. Hopefully we don't overshoot. 6 times 3 is 18. Carry the 1, 3, 4. Okay, so this is good. This gives me 3. So, okay, so I went ahead and did this long division because I needed the space underneath to do that. But I didn't have the space there. Okay, but now that I know the results, I know that the quotient here is 13 and the remainder is 3. So when you go down the river and you write 13, 3, 15, that's the wrong answer. You might be thinking to yourself, what? Well, I'll fix it. I'll put some commas. Okay, well, that's the wrong answer as well. We are changing to base 16. And if you remember about base 16, if I can find that piece of paper here. Here it is. We had different things here, so let's move this up here. We can see that 13 is actually D. So this is really D, and then 3 is 3, and 15 is F. So D3 F, this is base 16, and that's my answer. Okay, a little bit of an ugly problem. I have only done method 2. So let me get another piece of paper and see how method 1 works with this one. Okay, so I'll use method 1, so this is number 6, method 1. Okay. So we are changing 3,391 to base 16. So I have some carts. I have the 1 cart, the 16 cart. 16 times 16, we did that somewhere else in this lecture, and I believe we got 256. I remember doing that. So 16 times 16 is 256. And if you go times 16 again, I mean, that's just going to be some big number, 256 times 16. I really should walk across the room and get my calculator. 36, 33, what do we have? 12, 13, 14, 15. And then we have 6 and 5 and 2, 6, 9, carry that. Oh, look at that. That's going to be 4,096. I cannot afford one of those. So what do? We end up saying, well, I have $3,391. I cannot afford one of those, but can I get one of these? And the answer is, yes, you can. So let's put it in the cart. Now this is going to take forever because you can get a whole bunch of these, couldn't you? So one thing you might think of doing if you're doing the shopping method is to go 256 goes into 3391. Well, if you're going to do that, and you were avoiding the shopping method because you hate long division, this is the worst long division that I have in this lecture. But this would tell you how many of these items you can buy, and you're stuck back doing long division or subtracting 256 many times. So like if you decided like, oh, I want to do the long division, well, yeah, that stinks. So that's why some people are going to like just the long division way better, because on a problem like this, yuck. 83, I think. And then we bring down the 1, we say 256 goes into that, maybe 3 times. I mean, this is really out of a lot of people's comfort areas here. So we have 15, 16, and we have 6, 7. So 11 minus 8 is 3, but we borrowed. And so this thing, I mean, this guy borrowed from here, and now he's a 2, and this guy needs to borrow, and now he's a 7 and 12, and hopefully I did that right. So carry that, okay. So 63. So the deal is, you could have bought 13 of these guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, in which now you have $63. Whew! So $63, that's how much money you have, because I did the division and it tells me $63. That's the leftover, that's the remainder after buying this. So I'm not going to like subtract 256 13 times, I'm just going to do it this way. Now, I cannot get 4 of these, I think I can get 3 of these, and 16 times 3 is like 48. So I subtract, and wait, what is 16 times 3? It is 48. Okay. And then 8. Oh, this is because that's not a 5 there. 13 minus 8. Put a 7 there. It's really a 5 right there. Okay, and then borrow from the 6, so 1. Okay, so I have 16. I bought 3 16s and I have $15 left. So look, I'm going to put 15 of these in the cart. So as you can see, method 1 really let us down on this problem. I mean, look at this. This looks worse than that. Though some of you are like, no, that looks pretty bad because you put a cloud there and that scares me, but look at this. Any case, when you count all these little items, you have 13 here, you have 3 there, and then you have 15 there. And notice what we did on the other one, on the other page, we have 13, 3, 15. We changed them to D, 3, F. And so I'll just go ahead and say, okay, so you can get D, 3, F, base 16. Okay, so that's why people like method 2 better. Some people do. And some people still say, well, I don't care. I still like this method, even though sometimes this will happen. Let's go ahead and do problem number 7. Change 176 to hexadecimal. What is hexadecimal? Hexadecimal is base 16. Now this one is not as bad as the last problem. The last one was 3,391 and this one's only 176. I'm just going to use one of the methods this time. I'll use method 2. You could pause the video and see if you can do this problem. And I know you're thinking the last problem just spooked you. This one is not as bad. So 176, and I'm going to go ahead and throw 16 into it. 16 goes into 17. 1 times 16 is 16. We subtract, we get a 1, bring down the 6. 16 goes into itself. 1 times 16 is 16. We subtract, we get a 0. Now we got to remember, it's a remainder, so you have to put your 0 there. Now I'm going to say, well, 16 goes into 11. Well, it can't. So I'm done. I go down the river. There's not much of a river to go down. I have 11 and I have a 0. And we don't want to write 110 for our answer, and we don't want to write 11, 0 for our answer. We want to say, oh, well, remember hexadecimal. A was a 10, B was an 11, C was, I could stop right there because I could replace that 11 with B. We don't put the comma, and then we have a 0. B, 0, base 16. So that's how we change things from base 10 to hexadecimal. Okay, we're almost done with this section. It is a long section. The lecture is a little longer than some of the other lectures. Change 3, 4, I can't speak today. 2, 4, 3, base 5 to base 7. Okay, so how are we going to do that? What we're going to do is we've never changed from non-10 base to a non-10 base, and we're doing that for the first time. So I'm going to go ahead and give you the planet analogy. So here is planet 5. And here is planet 7. You're on planet 5, and this is the number that you see on planet 5, and you're like, oh, I'm doing base 5, and I'm trying to get to base 7. So a natural thing to do is to make a stopover on Earth, which is really planet 10. And I know you're thinking Earth is planet 3, but come on, don't ruin my analogy. And so that's what you're going to do. Your strategy is to go like this, and then fly off to that planet. So you get a few of these at the end of all of the problems in your homework. So let's see if we can do this. The problem is I just wasted all the space on my picture. Oh well. Okay, so now we got to make sure we know how to do these problems. And the last 7 problems we did, we were going from home planet to a weird planet like hexadecimal or binary or whatever. And so that's the one where you're doing shopping or doing long division. So this is shopping or long division, which was actually more difficult than the ones where we went from like base 5 to base 10. This was just multiplication and adding. I'll just say multiplication. So the way I remember this is it's easier coming home because you're more comfortable with what's in your house. And when you leave your home, it's going to be a little more complicated, long division or shopping. So let's go ahead and do this problem. You know what? I believe I can fit it on this piece of paper. So we're first going to go over here. I put 2, 4, 3. And since I'm coming from planet 5, base 5, I'm going to put a 1 above. And then 1 times 5 is 5. 5 times 5 is 25. I'm going to go ahead and multiply. 2 times 25 is 50 plus 4 times 5 is 20 plus 3 times 1 is 3. So when you add those all together, looks like you get 73. But since this is base 10, we're going to say it's 73. So we're familiar with that number. Now, I'm going to go change 73 base 10 to base 7. Using one of those methods, I'm going to go ahead and use the long division. You can use whatever method you want. So my long division would be 73. 7 goes into that. 7 goes into 7 one time. 1 times 7 is 7. Subtract, get a 0. Bring down the 3. 7 goes into 3. Well, it doesn't. 0 times 7 is 0. Subtract, the remainder is 3. 7 goes into 10. Well, 7 goes into 10 one time. 1 times 7 is 7. The remainder is going to be 3. And so now we know on planet 7 the number is 133. So when you see problems like this at the end of your homework, these are 2 problems in 1. And so our official answer should say 133 base 7. Okay, let's do the last problem. This problem actually could be skipped. You're not going to have to do anything like this in your homework, but some of you are going to find that this is really cool. We're going to count from 0 to 7 in binary. Okay, so let's count from 0 to 7 just in base 10. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, now 0 in binary is going to be 0. 1 in binary is going to be 1. I am actually going to put some shopping carts up. So we have 1, 2, 4. Okay, so because I'm going from base 10, I'm leaving home, which is, it's harder to do. And now, how can I put items into these to add up to 2? Well, if I just have $2, I'll put an item there and nothing there. So it would be 1, 0. So 2 is 1, 0. You can also do long division on these, but I'm actually doing the shopping method. 3, so if I had $3, so I'm doing like 8 problems in a row. If I had $3 and I was going to buy things, I can get a 2 and I can also get a 1. So I would have 1 item there and 1 item there, which means 3 in binary is 1, 1. 4 in binary, so what can I get with $4? I could get one of those items and that's it. So I would have like a 1, 0, 0. 1, 0, 0. 5 in binary, I can buy a 4 and I can buy a 1, which is 1, 0, 1. 6 in binary. 6 in binary would be a 4 and a 2. And then that's a 0, so we'd have 1, 1, 0. 7 in binary would be, I would just be buying all of those. A 4, a 2, and a 1, which is 1, 1, 1. Okay, remember when I said you can pad a number with zeros? I had 007 written up there. Well, that's what I'm going to do with the first 4 numbers. I'm going to pad them with zeros. So 11, well, it's not 11, it's 1, 1. I'm going to put a 0 in front of it. And then I'm going to put a 0 in front of this one. And then I'm actually going to put 2 zeros. This is like the 007 thing, except this is 001. And then this is 3 zeros. Does this remind you of anything that we did in this class? And hopefully it does. It probably reminds some of you of the truth table, where 0 is true and 1 is false. Do you see how it alternates by 1s there? And when it alternates by 2s in the middle column and alternates by 4s in the first column. When we were writing up our truth tables with 3 letters, so this would be 3 letters in our truth tables, we were actually counting in binary. So that should maybe amaze you, or maybe it doesn't amaze you. Let's go ahead and do our puzzles. There are 10 kinds of people. Those who know binary and those who don't. Well, maybe we shouldn't be saying 10, because now we know about binary. 10 is really what? It's really 2. And then we wouldn't say 10, it's 1, 0, so 2. There are 2 kinds of people. Those who know binary and those who don't. Ha 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 ha. A Roman walks into a bar, holds up 2 fingers, and says, 5 beers, please. So look at my 2 fingers. What do my 2 fingers look like? A V, which is really 5. Okay? Now, I didn't promise you laughs. You didn't sign up for the class and then my syllabus, it did not say, I'm guaranteeing you laughs. So if you feel betrayed and you say, oh, that was really bad, well, no one said you were going to be laughing during these videos. Let's go ahead and show you the smart cards. We're going to take a look at our last little trick here. These are called smart cards, and they have numbers from 1 to 63. Now, the whole illustration of this is really going to stink because it's better to have interaction on this. But what you do is you show this sheet to your friends, and you say, pick a number between 1 and 63. But do not tell me the number. So they can actually include 1 or 63, but they're supposed to pick a number. And so the trick is, your friend is supposed to tell you where their number appears on. So suppose your friend said this. So I'll just have this one right here. Your friend said, oh, my number's on the blue card and the orange card. And almost instantly, you should be able to tell them the number. The number is 18. Now what does that mean? Well, you see 18 there on the blue card. You see 18 on the orange card. And if you really look at the other cards, you will not see an 18 on those cards. So I'm going to go ahead and do another one. The next one is, suppose your friend says, oh, my number is on the green card, the red card, and the yellow card. Green card, red card, yellow card. You're supposed to figure out really quickly that their number is 13. Now, you're probably thinking, well, Joe, you prepared this, so you knew that's what the number was. Now, I'm going to show you the trick. Here is the trick. When your friend says, my number is on the green card, the red card, the yellow card, well, the green card, what you look at is that first number, green card. And the red card, you look at that first top left number. And the yellow card, you look at that top left number and you just add those numbers. So look, 8 plus 4 plus 1, that gives you 13. And we actually didn't do this, but you see 13 on the green card. You see 13 on the yellow card. You see 13 on the red card. But when you look at the orange card, the blue card, and the purple card, you do not see 13. So that is how the trick works. And on this one, when someone says, oh, blue and orange, we'll go back to this and remember the number was 18. All I did was add up 16 plus 2. So I'm going to see if you can do this. I'll try not to cover up the top left number because those are the ones you're adding. So I have picked a number that is only on these cards here, purple, green, yellow. So I would like you to tell me what that number is, and you should be able to do it pretty quickly. You're adding some numbers together. So purple, so I'm going to go ahead and actually write this down now. So purple, green, so there's purple, I'm pointing to the 32, there's green, and yellow. So you're going 32 plus 8, which is 40. 40 plus 1 is 41. So that's how you do this trick. Now, more interesting is, why does this trick work? What is really happening? How were these smart cards created? Let's get into that. So I'm going to go ahead. So what I've done is I've pretty much cut out the cards. And I can't show them all because it will go off the image of the camera. And then I can zoom out, but then the numbers get really small. Okay, let's do this example here. And they said, when I told you my number was on the purple, green, and yellow, and you guys told me that it was 41, or I said it was 41, I don't know. I said my number is on the purple, on the green, and on the yellow. Which means that my number was not on the blue, was not on the red, was not on the orange. So if I had the cards lined up like this, and we were doing this, instead of saying purple, green, yellow, that's a lot of syllables, I can say the cards are lined up, and I'll just say 1, if I see my number on that card, and 0 if I don't. So look, 1 0 1 0 0 1. What does that look like to you? That looks like a binary number. To convert binary to base 10, look at this. 1 2, and then look what you see up here. 1 2 4 8 16 32. So when you're doing this trick, whether you know about binary or not, and I tell you purple, green, yellow, you are converting a binary number to base 10, because what did we do in this? We said, oh, well, the number is 32 plus 8 plus 1. 41 is the number. So if I told you another configuration, let's say I said my number was on all the cards, then it would be 1 1 1 1 1 1, and then you would just add those up. You would be converting 1 1 1 1 1 1 from binary to base 10, and you'd end up getting 63. And we can't see it, but 63 does appear in the bottom quarter of each card. See? Okay, well anyway, you can see that for yourself. So these are called binary cards. Now, how were they created? Well, I took each of the numbers, 1 to 63, and I wrote them out in binary. So like a number like 18, you know, when it doesn't appear on the purple card, there would be zeros there, and there would be a 1 there, etc. So I padded things out with zeros. And then everywhere there was a 1, like for instance this one, 41, then I would go ahead and put 41 wherever there was a 1. So there's a 1 on the purple card, a 1 on the green card, you know, a 1 under the green card, and a 1 under the yellow card. So then you notice there's a 41 there, so I put it on that one. I didn't put it on the orange card, or I can't even pick these cards up anymore. I didn't put a 41 on the red card, then I put a 41 on the green card. There's not one on the blue card, and there is one on the purple card. So that concludes our lecture from 4.3, Changing Bases. This was a long lecture. Do your homework. Have a good day. I'll see you in the next video.